Earth's oceans were once green, says Study of Volcanic Waters. This is by Cedric John from The Conversation. Nearly three-fourths of Earth is covered by oceans, making the planet look like a pale blue dot from space. But Japanese researchers have made a compelling case that Earth's oceans were once green in a study published in Nature magazine. The reason Earth's oceans may have looked different in the ancient past is due to with their chemistry and the evolution of photosynthesis. As a geology undergraduate student, he said, I was taught about the importance of a type of rock deposit known as the banded iron formation in recording the planet's history. Banded iron formations were deposited in the Archean and Paleoproterozoic eons, roughly between 3.8 and 1.8 billion years ago. Life back then was confined to one-cell organisms in the oceans. The continents were a barren landscape of gray, blue, and black rocks and sediments. Rain falling on continental rocks dissolved iron, which was then carried to the oceans by rivers. Other sources of iron were volcanoes on the ocean floor, and this iron will become important later. The Archean eon was a time when Earth's atmosphere and ocean were devoid of gaseous oxygen, but also when the first organisms to generate energy from sunlight evolved. These organisms used anaerobic photosynthesis, meaning they can do photosynthesis in the absence of oxygen. It triggered important changes as a byproduct of anaerobic photosynthesis is oxygen gas. Oxygen gas bound to iron is seawater, and oxygen only exists as a gas in the atmosphere once the seawater iron could neutralize no more oxygen. Eventually, early photosynthesis led to the Great Oxidation Event, quote-unquote, a major ecological turning point that made complex life on Earth possible. It marked the transition from a largely oxygen-free Earth to one with large amounts of oxygen in the ocean and atmosphere. The bands of different colors in banded iron formations record this shift with an alternation between deposits of iron deposited in the absence of oxygen and red oxidized iron. The case for green oceans. In recent papers, case for green oceans in the Archean eon starts with an observation. Waters around the Japanese volcanic island of Iwo Jima have a greenish hue linked to the form of oxidized iron, Fe3. Blue-green algae thrive in the green water surrounding the island. Despite their name, blue-green algae are primitive bacteria and not true algae. In an Archean eon, the ancestors of modern blue-green algae evolved alongside other bacteria that use ferrous iron instead of water as a source of electrons for photosynthesis. This points to high levels of iron in the ocean. Photosynthetic organisms use pigments, mostly chlorophyll, in their cells to transform carbon dioxide into sugars using the energy of the sun. Chlorophyll gives plants their green color. Blue-green algae are particularly because they carry the common chlorophyll pigment, but also a second pigment called phycoerythrobilin, PEB for short. In their paper, the researchers found that genetically engineered modern blue-green algae with PEB grow better in green waters. Although chlorophyll is great for photosynthesis in the spectra of light visible to us, PEB seems to be superior in green light conditions. And before the rise of photosynthesis in oxygen, Earth's oceans contained dissolved reduced iron, iron deposited in the absence of oxygen. Oxygen released by the rise of photosynthesis in the Archean eon then led to the oxidized iron in seawater. The paper's computer simulations also found oxygen released by early photosynthesis led to a high enough concentration of oxidized iron particles to turn the surface water green. And once all iron in the ocean was oxidized, free oxygen, O2, existed in Earth's oceans and atmosphere. So a major implication of the study is that pale green dot worlds viewed from space are good planets to harbor early photosynthetic life. The changes in ocean chemistry were gradual. The Archean period lasted 1.5 billion years. This is more than half of Earth's history. By comparison, the entire history of the rise and evolution of complex life represents about an eighth of the history of the Earth. Almost certainly, the color of the oceans changed gradually during this period and potentially oscillated, and this could explain why blue-green algae evolved both forms of photosynthetic pigments. Chlorophyll is best for white light, which is the type of sunlight we have today. Taking advantage of green and white light would have been an evolutionary advantage. Ocean couldn't change color again. The lesson from the recent Japanese paper is that the color of our oceans are linked to water chemistry and the influence of life. We could imagine different ocean colors without borrowing too much from science fiction. Purple oceans would be possible on Earth if the levels of sulfur were high, and this could be linked to intense volcanic activity and low oxygen content in the atmosphere, which would lead to the dominance of purple sulfur bacteria. Red oceans are also theoretically possible under intense tropical climates when red oxidized iron forms from the decay of rocks on the land and is carried to the oceans by rivers or winds. Or if a type of algae linked to red tides came to dominate the surface oceans. These red algae are common in areas with intense concentration of fertilizers such as nitrogen. In the modern oceans, this tends to happen in coastal coastlines close to sewers. As our sun ages, it will first become brighter, leading to increased surface evaporation and intense UV light. This may favor purple sulfur bacteria living in deep waters without oxygen. And it will lead to more purple, brown, or green hues in coastal or stratified areas, with less deep blue color in water as phytoplankton decline. Eventually, oceans will evaporate completely as the sun expands to encompass the orbit of Earth. At geological timescales, nothing is permanent, and changes in the color of our oceans are therefore inevitable. This is from the conversation here under Creative Commons by Cedric John, Professor and Head of Data Science for the Environment and Sustainability, Queen Mary, University of London, on Science Alert. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.